Right, so without further ado, let's start our class for today. So this is our last chapter for microprocessor courses. Okay, so now we are going to look at module 13. So in this module 13, okay, you're going to learn about serial communications. And then after that, you're going to write a C program based on the serial communications. Okay, now let's look at the serial communication overview. Okay, what is a serial communication? Okay, in ARM processor, a serial and parallel communication are two fundamental methods for data exchange between the device. In the ARM processor, there are two methods in order to communicate between one device to your computer or from computer, or sorry, not computer, from your device to the processor and from the processor to another device, or from one device to another, right? So there are two ways to do it. One by using a serial communication, okay, using a parallel communication. Okay, so what is serial communication? Okay, serial communication is used to transmit a data bit at a time over a single channel or a wire. So this one here is very efficient for a long distance communications and minimize number of physical connections. Okay, so this serial communication is used if you have a very long distance communication. And example of the serial communication is SPI and I square 2. So in this class, okay, we will cover how to write program using the UART and the USART. Okay, then the second communication is a parallel communication, which is this parallel communication will transmit multiple bits, okay, simultaneously over multiple wire, okay, compared to the serial. Serial, every time you're going to do a communication, you need to send the data serially, one bit by one bit. But for the parallel communication, okay, you can send a multiple bit at at the same time. Okay, and this serial parallel communication is faster. Okay, for the large data transfer, but it's only cover a short distance. Okay, if you have a short distance communication, then you can opt or you can use a parallel communications. Okay, because it's very fast compared to the serial communication. An example of the parallel communication, which is LCD interfaces. Okay, so LCD interface is one of the examples of the parallel communication out there. Right, so now we're going to look at the basics of the serial communication. So when the microprocessor communicate with the outside world, okay, which is the processor want to communicate with outside worlds, okay, this it usually provide the data in the byte size of chunk. Okay, byte size of chunk is a 8-bit data lah. Okay, so for the parallel transfer, okay, a 8-bit data is transferred at the same time. Okay, while for the serial transfer, 8-bit data is transferred 1 bit at a time. Okay, so parallel transfer, you can send out 8-bit data at the same time. Okay, no problem. But serial transfer from 8-bit data, you need to divide to transfer 1 bit by 1 bit. So here, example of the serial transfer and parallel transfer. Okay, you can see here for the serial transfer and parallel transfer, you need to have a sender. Okay, sometimes we call it as a transmitter. And then you need to have a receiver, right? So for the serial transfer, you can see only one of data is transferred at one time. Okay, compared to the parallel transfer, you can see here a total of 8 bits data is sent from sender to a receiver. Okay, so this is the difference lah, okay, between the serial and parallel communication. All right, so now we're going to go more deeper on the basic of the serial. So for the serial data communication to words, okay, the byte, okay, must be grabbed from the 8-bit data bus, okay, of the microprocessor. So 8-bit data from the microprocessor need to be converted, okay, to the serial bits using a parallel in serial out register. Okay, since you have a 8-bit data, and then you need to set it bit by bit. So what happened here is from this 8-bit data, it need to be converted to the serial bit by using the parallel in serial out shift register. Figure below here is a parallel in serial out register. As you can see here, you have multiple bits coming from the inputs. Okay, assume D is a data. Okay, you have a 4-bit data, for example, for this figure here. So you have a 4-bit data, and this 4-bit data will go to the register, okay, parallelly. And then what happened here is, then on the output side, okay, it will be converted to the serial data. Okay, you have a parallel data going into the register, and from the register, it will go out as a serial data. Okay, so since the data being sent out to the over the communication line is a serial data, so you need to have a receiving end or receiver to convert back from the serial to the parallel data, okay, which is from the 1 bit of data to a 8-bit of data. So here at the receiving ends, okay, we need to have another register called a serial in parallel out shift register, which is used to receive the serial data and pack it into 1 byte of data or in 8-bit data. So this is the figures lah of the register at the receiving end. Okay, which is from here we can see here the data coming in. Okay, is a serial data, which is a 1 bit of data. Then after that, by using this register, it will convert into the bit of, 1 byte of data, right? So when the distance is short, okay, the digital signal can be transferred as it is on a simple wire and require no modulations. Okay, you can use this serial communication without any need to
Screen
have.
doktor sekat-sekat.
Screen yang mana ya?
Yang doktor share ni.
Oh ya ke? Sekejap I share it back. Wait eh. Okay, so now we're going to resume back our class. Okay, so here as we can see here, okay, so this is the registers lah. Okay, that is convert back from the serial data to a 8-bit data, which is we have a serial coming in to this register, okay, bit by bit. And on the output side, okay, it will convert to a byte of data or 8-bit data. But in this example, it's a 4-bit data lah, because we have a 4 register, 4D flop. Okay, if you're going to have a 8-bit data, so you need to have another, you need to add another 4D flip-flop to make it as a 8-bit data, okay, to merge back from the serial data to 8-bit data. Okay, so this serial communication also can be used as a short distance communication, which is for the short distance communication. Okay, the digital signal can be transferred as it is on a simple wire and require no modulations. Okay, means that you can simply send the digital signal without need to do any modifications. Okay, but if you're going to you send the data for the long distance, okay, which is a long distance data transfer, contohnya telephones, okay. So the serial data communication requires a modem. Okay, you need to have a modem to modulate the signal. Okay, you need to modulate the signal, which is the digital signal from 0 to 1. Okay, need to convert to the audio tones. Okay, because we're going to send to over the long distance. So in order to make sure that the data is not being lost, so you need to use the audio tones. Okay, then the data before putting it on the transmission media. Okay, so from the digital, convert to the audio tones. Then on the receiving part, you need to demodulate. Okay, you need to convert back from the audio tones to the digital signal at the receiving end. So this is the mechanisms lah. Every time you're going to send a digital signal or over a long distance, while for the short distance, okay, you can simply send the digital data without need to do any modifications. Okay, and for the serial communication, there are two types of the serial communication. One, we call it as a synchronous communication or synchronous serial communication. The second one is a asynchronous serial communication. Okay, what are the difference between the synchronous communication and asynchronous communication? For the synchronous communication, clock is transmitted along with the data. Means that you need to, a part of you send the data over the line, you need to also, you require to submit the clock signal as well. Okay, so both sender and receiver share a common clock signal. So this is how the data can synchronously transmit and receive by transmitter and receiver. Okay, so the data bits are sent in a stream without start or stop bit. Okay, by using the asynchronous communication, you no need to requires to have this start or stop bit. But if you use an asynchronous communication, you require to have this bit, okay, to let the receiver know, okay, when the bit is started and when the data already finished, okay, sent from the transmitter to receiver. Okay, and this is an example. This is a figures lah of the serial communication between two devices using a shared clock source. Okay, as we can see here, we have a clock input, and at the same time, the data that you're going to transmit from device A to device B. Okay. Next is asynchronous communications. Okay, we're going to look at the asynchronous communication. For asynchronous communication, no clock transmitted with the data. So means that you send the data without any clock signal. Okay, and it does not rely on the shared clock. So no need to have a shared clock. But for this asynchronous communication, okay, you need to have the start and stop bit that frame each data packet so that the receiver know, okay, the receiver know, okay, or receive the correct data. Okay, and each packet can be sent independently. Okay, so here, as we can see, there is no clock input from these figures here. So first, what happened here is you can see D is where the ideal, okay, D is the ideal state, okay, means that no transmission occurs at this state, all right, and then the transmission begin with a start bit. So you have the start bit over here. So this is the start bit. Okay. So how the CPU know? Okay, the transmission is started. Okay, the processor know the transmission is started when it sends the negative trigger. Okay, so this is the negative trigger. So negative is trigger is a falling edge lah. Okay, by looking at this diagram here, it is a falling edge. Okay, so the negative edge is detected by the receiver. And after a few seconds, okay, which is in this bit, in this example here, after 1.5 bit period, okay, the sampling of bit will begin. Okay, once the CPU know that, okay, I send the negative edge triggered here, a falling edge, then after 1.5, the next signal will be the data that will be sent out from the transmitter. So this is how the receiver know lah, okay, which data is sent by the receiver. All right. So since the serial communication is we're going to send a 8-bit data over the serial communication, so you need to have a up to 8-bit lah. Okay, a 8-bit data will be sent out and will sample by the register just now, okay, which is it changed from the parallel to the serials, okay. So the least significant bit, the LSB, is typically transmitted first over the line, followed by the last one is a most significant bit. And sometimes optional parity bit is transmitted. Okay, so parity bit is transmitted in addition to this data here to check, okay, for error. If there is error, then the receiver know lah. Okay, based on the parity bit that will be sent out to the receiver. And then the transmission is ended by a stop bit. Okay, you can see here, this stop bit is lasted 1.5 bit. Okay, when the receivers sends this, the stop bit duration is 1.5 bit. So the receiver know now the transmission is complete. Okay, so this is how the asynchronous communication works. Okay, moving on to this slide here. All right, so this slide show the 3 methods of the basic the serial communication, or sometimes we call it as a transmission mode of the serial communication. Okay, first it's a simplex transmission. Okay, what is a simplex transmission? The simplex transmission is where the data flow in one direction only. Okay, means that you have device 1 act as transmitter, while device 2 act as a receiver. Okay, and the data is a one-way transmission. Okay, from transmitter to receiver. Okay, the receiver cannot transmit back the data to the transmitter, or device 2 cannot send back the data to device 1. Okay, so that's what we call as a simplex transmission mode. Okay, example of the simplex transmission mode is keyboard and monitor. Okay, so keyboard is your device 1, which is your transmitter, while the monitor is a device 2. Okay, which is keyboard only can send the data to be displayed on the monitor, which is your device 2. Okay, the second transmission mode is half duplex transmission. Okay, for the half duplex transmission, the data flow in both directions. Okay, so data can be send from device 1 to the device 2. Then after the device 2 can send back the data to device 1. But, okay, for half duplex, only one direction at one time. Means that when device 1 send the data to the device 2, at that moment, device 2 cannot send the data back to device 1. Means that the device 2 need to wait until the device 1 finish sending the data. Then after that, it can send another data to device 1. Okay, so the devices that turn sending and receiving a data. Okay, example of the half duplex transmission is walkie-talkie. Okay, means okay when you use a walkie-talkie, okay, you have a two walkie-talkie. One is for the you give it to your friends, and once you use it yourself. Okay, when you try to speak to your friend, try to talk to your friends, okay, your friend only can hear what you try to communicate. Okay, what you try to say. Okay, he cannot talk back to you. Okay, at the same. Once you finish, okay, talk to your friends. Then after that, he can reply. Okay, and send. Okay, speak back to you while you are listening. Okay, so this is the half duplex transmission. Okay, and the third transmission mode is a full duplex transmissions. Okay, which is the data flow in both directions simultaneously. Okay, so the keyword here is a simultaneously. Okay, so sending and receiving occur at the same time. So contoh using a full duplex transmission mode are telephone. Okay, while you are talking over here, your friend also can talk back over there. Okay, you can both can talk at the same time. Okay, so that that is the full duplex transmission mode. Okay, any question up until here? Ada soalan tak? Before we move on to the UART and USART register.
Is it running?
Okay. Okay, if no question, then we move on to UART and USART register. What are the registers that you need to know before you write the serial communication program? Okay, so let's look at what is a UART, what is a USART. Okay, so the UART stand for universal. U is a universal. A is a asynchronous. R is for the receiver. T is a transmitter. So UART is actually a universal asynchronous receiver transmitter. So it's a hardware communication module that enable asynchronous serial communication. So by using the UART, you can communicate between one device with another device asynchronously. So the key feature of the UART here is, since it is asynchronous, so no clock signal is shared between the transmitter and receiver. Okay, no need to have the clock source. The data is framed using a start bit, stop bit, and optional parity bit, as I mentioned earlier. Okay, your data will be at encapsulated using the start bit, okay, to indicate that the transmission is starting. Then after that, if you're going to check for the error, you can put the parity bits side of the data. And when the transmission is end, then you need to have a stop bit to indicate that the transfer is complete. Okay, and UART is a full duplex mode transmission. Okay, full duplex mode means that you can transmit and receive at the same time. Okay, mean both device A and device B can transmit and receive at the same time. And UART require only fewer wires, only 3 wires are required for the UART communications. Okay, one is a transmitter, the wire for the transmitter. The second one is for the wire for the receiver, and the third one is wire for the ground. Okay. Meanwhile, okay, for the USART, okay, USART stands for universal. S is a synchronous, A asynchronous, receiver and transmitter. Okay, so what happened here is the USART can perform both synchronous and asynchronous serial communication. Okay, because it have the serial and it have the synchronous and asynchronous at the same time. Okay, and the key features of your USART here is when it's run on the synchronous, okay, when you try to do a synchronous communication, okay, it will involve a shared clock signal between devices. Okay, every time the USART try to communicate synchronously, so it need to have a clock signal between device A and device B. So that's why you can see here, okay, you need to have the clock input, clock source here, okay, for the device A and device B. And when it is run under asynchronous mode, so the data is framed using a start bit, stop bit, and parity bit. Okay, similar to UART communication. Okay, and again, SAT and UART are full duplex mode transmission, and this USART requires additional lines or additional wires called a clock wire for synchronous mode. Okay, a part of it has the transmitter line, receiver line, and ground line. It also need to have a clock line whenever it run under the synchronous mode. Okay, so high speed communication compared to UART. Okay, if you're going to have a slightly high speed communication, you can use the USART. Okay, if you're going to have a slower communication, you can use the UART, right? In terms of the programming, okay, every time you write a programming, okay, in the previous chapter, we need to know what registers are involved. Okay, similar to the UART and USART programming, there are 3 group of register in USART and UART peripherals that you need to know. Okay, first is a configuration register. Okay, the configuration register where you're going to initialize the USART or UART, okay, configurations. Okay, and the parameter that you're going to configure in this register, such as a baud rate. Okay, what are the baud rate that you're going to use? Okay, word length, how long the data you're going to send out. Is it a 8-bit data or maybe a 9-bit data? Okay, then a stop bit. What are the duration of the stop bit? Some stop bit have a 1.5 bit duration. Some stop bit have a 1.0 bit duration. So it depends on the configurations here. Okay, if you set the stop bit is 1.5 bit configuration, so every 1.5 bit, the receiver know, okay, the transmission already ended. And the configuration of the interrupt serial communication. Okay, if it is needed lah, if you're going to use the interrupt for the serial communication, so you need to configure the interrupt as well. Okay, so the registers are the baud register. Okay, you need to know the baud register. Then the control 1 register and control 2 register. For the configuration of for the UART and USART configuration, you need to know 3 registers. Okay, baud, control 1 and control 2. Okay, moving on to the second register that you need to know as well. Okay, which is we call it as a transmit and receive register. All right. So to send the data, okay, we can use the transmit data register, okay, to receive the data. Okay, all the data will be received in, will be stored inside of the received data register, okay. And last but not least is the interrupt status register. So this register contains some flag, okay, which show the state of the sending and receiving the data. Okay, it will indicate lah whether the transmission is complete or not. Okay, so the flag will be updated accordingly. Okay, when the transmission is complete, the flag will be set. If the transmission is still not complete, the flag will be 0. Okay, similar to receiving, when the device be from still receiving the data, okay, the flag will be 0, and when finish, the flag will change from 0 to 1. Okay, so the register, okay, for the interrupt and status register, we call it as the USART ISR. Okay, USART interrupt and status register. Okay, now we move on to the very first register. Okay, so this is important. Okay, so every time you're going to use a USART, or every time you're going to use a GPIO, every time you're going to use the interrupt, you need to enable the clock of that particular peripheral. Okay, for example, for UART and USART, okay, you need to enable the USART or UART clock. Okay, similar what we did in the GPIO lah. Similar what we did in the interrupt programming. So you need to enable the clocks. But this one, we call it as a USART clock. So where you're going to enable the USART clock, there are two locations to enable the USART clock. One at APB1 ENR register, and the second one is at APB2 ENR register. Right? So it depends lah what UART and USART that you're going to use. Okay, so to enable it, to enable the clocks, you need to give 1. Disable, give 0. Okay, now we're going to look at the APB1 ENR. So what are the register that you're going to look at? Okay, what are the bit that you need to focus on this APB1 ENR? Okay, for the APB1 ENR, the bit that you need to look at here is bit 20. Okay, so 20 is for your UART 5. Okay, if you're going to use a UART 5, okay, you need to enable this bit. Bit 19, okay, so this is for the UART 4. Okay, so if you're going to have the asynchronous communication, okay, you can choose whether you're going to use a UART 5 ataupun UART 4. Okay, to enable the clocks, you need to enable at this bit 20 and bit 19. Then USART 3 at bit 18, as well as a USART 2. So this is for the synchronous and asynchronous communication. Okay, you can choose either to use the USART 3 ataupun USART 2, which is located at bit 18 and okay. That okay, you just ignore. Only focus on this 4 bit. Okay, for APB1 ENR register. Okay, so as I mentioned, bit 20 and to bit 19. So this is for asynchronous communication. But for bit 18 and bit 17, this is asynchronous and synchronous communication. Okay, so this is for the APB1 ENR lah. Okay, then the second clock register that you need to enable here is a APB2 ENR. And so APB2 ENR also have the USART clock, okay, which is, as we can see here, okay, you need to enable at bit 5 if you're going to use the USART seed, ataupun bit 4 if you're going to use the USART 1. Okay, on these two bits that you need to enable. Okay, for example, okay, I'm going to use the USART 1 for my communications. So I just enable at this bit 4 inside of the APB2 ENR register. Okay, what about APB1 ENR register? Okay, no need to do anything. Okay, because I only use the USART 1 for my communication. Okay, and here, if you, this APB2 ENR also used when you're going to do the interrupt programming. Okay, remember back the sysconfig. Okay, so every time you're going to do an interrupt, you need to enable this as well. The sysconfig configuration as well. Okay, so for the USART, we only focus on these two bits lah, bit 4 and bit 5 inside of the APB2 ENR, depending on the communication that you're going to use lah. Okay, if you use a USART, if you're going to use the USART 2, then the clock must be enabled at this register. Okay, at this APB1 ENR register. So USART 2 is at this location, bit 70. All right. That is to enable the clock of USART. Okay. Next, register is a baud rate register. Okay, it's a baud register. Sometimes you use the USART BRR. Okay, BRR stands for baud rate register. Okay, the USART BRR is used to configure the baud rate for the USART and UART communication. So every time you're going to set a baud rate of your communication, okay, so make sure that you configure this BRR register. So this baud register will determine the speed of the data transmissions, okay, between the device by specifying the ratio of the clock frequency to the desired baud rate. Is that you need to calculate. Okay, there are formula to do it. Okay, you need to calculate what is the speed of the data transmission, and that speed, okay, the speed of the data transmission you need to put inside of this location. Okay. Okay, only 16-bit users use it for the baud register. Okay, the first bit here is for the division fraction. Okay, you can see here, bit 0 until bit 3 is for division fraction. So what the value that you get from the calculation, okay, the fraction value of the calculation will be stored here. Okay, this is a fraction lah. Okay, the perpuluhan, the number perpuluhan from the calculation will be stored here, while the integer from the calculation will be stored in this bit 4 until bit 50. Okay, so how to do a calculation? Okay, to do a calculation, you need to use this formula. Okay, so the formula says that transmitter receiver baud equal to f clock. So this is the speed of the processor. Okay, f clock, the speed of the processor, and then 8 times 2 minus over 8. Okay, and times USART diff. Okay, the USART diff is the baud rate lah. Okay, what is the baud rate that you're going to use? Is it a 9,600? Okay, is it a 12,000, or depend on the baud rates lah that you're going to use? And the over 8 here, okay, will be determined by either you're going to use a oversample by 8 or oversample by 16. Okay, if you use the oversample by 8, so the over 8 here, you need to replace with 1. Okay, so 8 times 2 minus 1 is equal to 1 lah. 8 times 1, 8, and then darab dengan multiply with the baud rate. Okay, if your data is going to oversampling by 16, so the over 8 here you need to replace with 0. So what happened here? 8 times 2, which is a 16, then after that you need to multiply with the baud rate. Okay, once get the result, okay, the result will be splitted into integer and fractional part, and then you need to send this result to this register. Okay, when you get the result, send the result into this register. Okay, the fraction will be put from bit 0 to bit 3, while the integer, okay, you're going to put it from bit 4 to bit 50. Okay, so now let's look at the examples here. Okay, the examples. Assume the clock source of the processor is 60 megahertz. Okay, you have the STM32. The STM32 processor speed is 60 megahertz, and it's fed to the USART baud rate generator with the oversampling rate of 16. Okay, it says that the sampling rate will be sampled off by 16. Okay, next, find the value for the USART BRR register for the baud rate of 9,600, 90,200, 57,600, and 150,200. Okay, so now let's find out the 9,600 baud rate. Okay, what are the value that you need to give to your baud register? Okay, so the formula is TX RX baud equal to F clock, okay, divided by 8 times T over 8 multiplied by baud rate. Okay, so what is your F clock? The F clock is a 16 megahertz. Okay, this is your processor speed. Okay, times with 8. Right, and then 2 minus 0. Why 2 minus 0? Because here you can see, okay, the data will be oversampled by 16. Okay, when the data is oversampled by 16, you can see here, okay, the over 8 equal to 0 when you oversampling by 16. Okay, that's why over 8 I put 0 and then multiply with 9,600, and you will get 104,166. Okay, you can see you have two value here. It's an integer value, and the second one is fractional value. Okay, nombor perpuluhan. Okay, so the integer value here is 104 is a decimal. Okay, so from this decimal, you need to change to binary. Oh, sorry, to hexadecimal or to binary also correct. Okay, but we use the hexadecimal. 104, change it to hexadecimal. Okay, you will get 58, and while 0.166 change to hexadecimal. Okay, so how to do it? You need to multiply with 16. Okay, why multiply with 16? Because this is oversampled by 16 lah. So you need to multiply with 16, and you will get 2.656, and then we just round to the nearest value. So the value will be 3. And change it to hexadecimal. The hexadecimal for 3 is 3. Okay, after that, this value you're going to put it inside of the BRR. Okay, so put it inside of the BRR. So this is the BRR. the fraction part is 3, you just put 3 lah. Okay, the 3 is actually 0011. Okay, while the integer is what? The integer value just now 68. Okay, you just put here. Okay, 6, 8, and this one is 0. Okay, so this will be the value. Okay, inside of the USART BRR. Okay, in terms of writing the program, okay, in the program you can write USART BRR equal to 0x0683. Okay, any question up until here? Okay, we already calculate the value that you're going to put to your baud register. Okay, with oversampling rate of 60 and the baud rate is 9,600. Any question up until here? Okay,
No.
if no question, then we move on to look at the B here. Okay, now we're going to calculate what value that you need to send out to your baud register. Okay, again, use the same formula here. Okay, FC clock divided by 8 times 2 minus over 8 and multiply with baud. Okay, the FC clock is at 60 megahertz. 8 times 2 minus 0 lah. Why? Because it's oversampled by of 16. And now you need to change this value here. Instead of 9,600, now you need to multiply with 19,200. Okay, so after you multiply with 19,200, the value will be, okay, the value that you will get here will be 5208. Okay, so again, you have two value here. One is integer, the other one is fraction part. So for the integer, change it to hexadecimal, press the calculator, you will get 34. Okay, while this one here, okay, you need to 0.8 multiply by 16, get the value, which is 1.28. And then 1.28, get the nearest value here is 1. All right, and the value in hexadecimal also 1. Okay, then you combine, right? The USART BRR value that you need to give here is 0x0341. So this is the value. Okay. So for 57,600 and 150,000, okay, you calculate and get the value later. Okay, so next, moving on to the next slide. Okay, maybe this is our last slide for today. Okay, and the rest we will continue in the next class. Okay, so examples here. Okay, assume that the clock source is 60 megahertz, is fed to the USART baud rate generator with oversampling of rate of 8. Okay, now you can see the sampling rate is 8. Okay, you need to find the value for the USART BRR register for baud rate of 9,300, 19,200, and etc. Okay, again, okay, we need to use the formula. Okay, just now the formula says that TXRX equal to F clock divided by 8 times 2 minus over 8 and times with baud. Okay, the baud rates. Okay, let's say now we're going to find out what is the value for 9,600. Okay, so the processor speed is at 60 megahertz divided by 8 to what is the over 8 value? Okay, since this one here we sample by 8. Okay, when you sample by 8, then the value of the over 8 is 1. Okay, and then multiply with 9,600, and you will get 28033. Okay, so you have two part here. One is for the integer. Okay, the other one is fraction part. Okay, integer, change it to hexadecimal directly, then you will get 118. Okay, meanwhile, 33, okay, now 0.33 multiply with 8. Okay, you need to multiply with 8. No longer multiply with 60. Why is that? Because we do use the oversample of 8. Okay, that's why we need to multiply with 8. And then you will get 2.64 and round it to the nearest value. So you will get 3. And the value of your USART BARR is, when you write the program, equal to 0x0, okay, no, 1183. Okay, so this will be the value. Okay, and similar to the other examples, okay, you just change from 9,000 to 600 with the block dates. Okay, and after that, divide it to the integer and fraction part and get the hexadecimal value. And once you get the hexadecimal value, then put it inside of the BRR register. Okay, guys, and up until here before we